Good morning, students. Welcome to our AC Motors. In previous classes, we have discussed overall synchronous motor from starting its basic principles, constructions, working operation, some salient points of synchronous motor, advantages, disadvantages, and applications. In details, we have also calculated few problems how the power factor is improved with the help of synchronous motor. In this class, we are going to summarize total lesson, the salient points of synchronous motor. We can see this is one of the synchronous motor generally used in our industries. Now, let us see its salient points from its basic principles to applications point of view. Now, you can as you know that the synchronous machine is nothing but it consists of stator. It has a stator frame. Inside there is a slots in which there is a three-phase winding is wound at a distributed winding. The construction point of view, it is similar to alternator. Synchronous machine is nothing but it can be used as a generator, it can be used as a motor. The physical construction point of view identical as we've seen. That means based on the input, whether you are going to give the supply. So, for generators you are going to give is a mechanical is the input and electrical is the output. But whereas in motors, electrical is the input and mechanical is the output. Now, based on this one, we going to study the synchronous machine. Now, this is a stator. The stator has the stator frame. It is also material generally used high silicon content material to reduce the hysteresis losses, and these windings are distributed in distribution slots to get the sinusoidal waveform. Now, three-phase supply here we are going to give in case of our motor. Now, it has a rotor. The rotor has rotor winding. It is fed from outside a DC motor, DC alternator, DC supply. Now, in case of our motor, now whenever the three-phase supply is given to the three-phase stator winding, it produces a magnetic field of that is equal resultant flux with of phi r, phi y, phi b. So, we are going to get that is called 1.5 times of any one phase, maximum flux developed by any one phase. This produced resultant magnetic field is rotating in the air gap at a speed of synchronous speed ns, that is equal to 120 f by p, where f is the frequency, p is the number of poles. Based on this one, once it rotating in an air gap at a synchronous speed, this flux act as a one north pole, another is the south pole. Now once you are going to give the DC supply, this one, the rotor also produced its north pole and south pole on rotor side. As we know that north pole and north pole repel each other, south pole repel each other. Now the stator field, that is the rotating magnetic field, rotating at a synchronous speed, that is now even, so you are taking the one AC supply, the positive and negative, this one, during the positive off cycle. So at north pole a stator at the top and south pole at bottom, let us assume. After negative off cycle, then this becomes to the south pole, this becomes to the north pole. After positive cycle, once again it becomes to the north pole and south pole. It changing alternatingly. We know that the 50 Hz means that is the 50 cycles per second. 1 second, it is a 50 times it is changing. That means so north pole and south pole, north pole and south pole. So during this process, what will happen? So now the rotor which having the, so here you can, this is a, for example, if you take it, this is this is a north pole and this is a south pole of stator during the positive off cycle, and during the, at this condition, the rotor has this one, and this is a north pole and south pole of rotor. During the positive off cycle, it becomes, what will happen? The stator has the stationary part, a rotor is placed on a ball bearings. Then due to the similar polarity, this will try to move this direction, this try to move this direction, repel each other. After 90 degrees displacement, then is a negative, after negative off cycle, then what will happen? So once again, so this becomes to the, this is a south pole stator, this becomes the north pole stator, but whereas this becomes the same. So that means here you can see, so due to the repulsion, now this will becomes to the, here this position, for example here, this is a north, this is a south during the negative off cycle. So due to this one, it will attract each other, then it will comes to the clockwise direction. Next positive off cycle, once again it becomes to the same this value, this is a north, this is a south, and rotor will try to, so whatever that comes here, that will try to repel each other, north and south, it comes this direction. Next negative off cycle, this is a south, this is a north, and same whatever that one, so it is going to this one, north and south, attract each other. One times it is going anti-clockwise direction, clockwise direction, anti-clockwise direction, clockwise direction, it is immediate seconds, that 50 cycles per second. Due to the a large inertia of rotor unable to follow this sequence, hence this rotor is at standstill position only, at standstill. That means there is no rotation of rotor in the synchronous motor. Hence we can say that the synchronous motor is not self-starting motor. Inherently it is a not self-starting motor. Why? So because we have given the AC supply to the stator and DC supply to the rotor. Even so, three-phase supply given to the stator and plus minus, that is the DC supplies to the rotor. So two types of supplies is given to the our motor. Even then it is not starting initially. That's why it is a not self-starting motor. What is the reason? We have seen here. Then how to start this one? So we have the different starting methods. So what are the methods we have seen? So we have method the different the starting methods. So we will see that one. Generally this can be started by using the some small pony motors. So how you are going to? So here in this case, so what to do to start this one? Initially, so this is the stator and this is the rotor. Okay, so north pole and south pole. So here what will happen? So that purpose we are given to the some mechanical input to this one. And here is generating north pole and south pole stator. It is rotating in this clockwise direction, for example, at a speed of synchronous speed. Then if you are giving the mechanical input to the rotor also rotate. For example, whenever it becomes the south pole and this becomes the north pole. So here is a south pole, this is south pole, this is the north pole. So due to the opposite polarity, it is a interlock each other. And once it's rotated, this rotor also with the help of the other external means motor which has the higher speed of this synchronous speed. That means number of poles of this incoming motor should be less as compared to the synchronous machine poles. Hence the speed is more. Here once the motor input, mechanical input is given to the rotor also rotating in the speed of the rotating magnetic field speed. Once both are rotating at the same speed, once north pole and south pole and north pole of both stator and rotor, they magnetically interlocked each other. Once interlocked each other, then automatically, so whatever the rotating magnetic field of stator, you try to drag the rotor in the same direction with the same speed. Hence, the synchronous motor runs at a synchronous speed only. So, synchronous speed only. For example, what is the synchronous speed? Ns is equal to 120 F by P. For example, our motor is designed for the 4-pole machine. Okay. So, our given the Indian frequency is the 50 Hz. Then, what is the value? Calculate it. Ns is equal to 120 into F is the 50 Hz. Now, P is equal number of poles. How many poles? 4 poles. 4 ones are 4 threes are 3, that is equal 1500 RPM. It is rotating in the air gap as a rotating magnetic field. And at the same speed, rotor is now interlocked with this magnetic field. Rotor also rotates in the speed in the same direction of 1500 RPM. Okay, so that means now stator and rotor is interlocked. Now instead of standstill condition, now we started the motor with the help of by external means by using a small DC motor, or we can use the AC motor. Okay, so small AC motor or DC motor. So we can start it, and at the another type also we can use. So here by using the damper windings. What do you mean by the damper windings? Because already you know this thing. Now we are going to summarize it. So now here what is happening? The stator having the stator winding and 3-phase distributed winding. Now the rotor has pole, north pole, for example 2-pole machine, you take it pull to. Here what will happen? So this winding is given to this rotor, and the same time at the pole shoe, if you are seeing the pole shoe, if you are providing the copper bars inserted, just like squirrel cage rotor copper bars, that is here you are going to the pole shoe. Okay, you place the copper bars both sides. That means here what will happen? So both copper bar, this bar is going to this direction. For example, you take the pole shoe. Okay, so that is the one copper bar, another copper bar, another copper bar, another copper bar. Now what will happen? So now we can short the end and short the other end. Okay, this is a pole. Okay, now what will happen? So these copper bars are inserted in the one side. Now similarly, you insert the other copper bars this direction. What will happen? So due to the copper bars, the conducting bars, once so rotating magnetic field, whenever the three-phase supply is to the stator, it produces that is equal resultant flux rotating at a synchronous speed. This magnetic field rotating in the air gap cuts the rotor copper bars. This is the copper bars. Now what will happen? Due to this is a stationary position, this is a rotating position. There is a high relative motion between the stator field and rotor. Then as per the Faraday's laws of electromagnetic induction, it induces the current inside these damper windings. Once induces the short circuit at both ends, then what will happen? There is EMF induced in this one, the current is flowing. The current flows and produces its flux. This flux in such a way that as per the Lentz's law, what has happened? So always oppose the cause of its production. So what will happen? It's the relative motion between these two. Then automatically rotor will generate a flux and try to avoid the relative motion. Then rotor will try to move in the direction of the stator rotating magnetic field. Once it is rotating in the same speed, at that condition we are going to give the DC supply to the rotor winding. The rotor also produces a whole magnetic field, that is the stator north pole and south pole. Once due to the damper winding, it acts as an induction motor. It is the induction. Due to the induction, it induces a EMF. Due to the EMF, current is flowing. This current, due to the current, the flux is produced. This flux and this flux interaction takes place. The torque is developed. Due to the torque, rotor will rotate in the synchronous speed. At that condition, with DC supply is given to the rotor, then rotor also produces its own magnetic field. This magnetic field and the stator magnetic field interlock each other and it will run continuously. Once what will happen? Once the stator north pole and rotor south pole is running at a synchronous speed. Once both are running at a synchronous speed, interlocked each other, the stator magnetic field and rotor magnetic field coincide each other. At that condition, this and this are both running at the same speed. At that condition, what is the position of now the copper bars, that is the damper bars? In this case, what will happen? So stator magnetic field and rotor is both are running. The relative motion between the rotating magnetic field and copper bars are zero. As per Faraday's law of electromagnetic induction, so we require that to induce a EMF, we require the conductor is required, magnetic field is required, and relative motion is required. But in this case, there is a conductor is present, there is a magnetic field is present, but there is no relative motion, because relative motion between the rotating magnetic field of stator and damper windings in the rotor is zero. Then there is no EMF induced in this one. Just like now these copper conductors act as a simple some material, not inducing any type of EMF and not opposing anything. Only it will work initially when it is required to start the motor. So this is the starting up synchronous motor with help of different methods, by mechanical means, by damper windings. Okay, now we started what is the construction and why it is not self-started. If it is not self-started, how we are going to start the motor, we have seen. Okay, now after that, so what will happen? So now this is a theoretically we have seen. It has a stator, it has a rotor, and both are magnetically coupled, and their axes coincide each other. Okay, theoretically. Now, So here what will happen? Now, so what will happen if the stator, okay, so it has this one. Now the rotor, okay, the rotor, both are running at normal. Whenever 3-phase supply is given to this one, this is simply and the same time a DC supply also given to the rotor through the slip rings. This is a DC, this is a 3-phase supply. Okay, both are running at one speed, synchronous speed is running. Motor is working very good. Now that is a constructional point of view. Coming to our electrical point of view, what has happened inside the machine? As you know that in DC machine, what is a DC machine? The DC motor, this is a stator, armature is the rotor, that is the reverse. The north pole and south pole stationary DC supply, this is the armature as the carbon brusher, this is the armature. Okay. Now in this case at rotor at standstill condition, the EMF induced in the rotor is 0. So that is the back EMF induced in the armature is 0 at speed is equal 0. Once speed increases, back EMF also increases, then it opposes the applied voltage. That is the induced. Suppose for example the motor, you can take it. So plus minus the voltage applied. Then what is happen? Current. The current I is equal to, that is a V minus EB by, that is equal RA. That is the in case of the DC. That means here the back EMF is directly proportional. What is the formula? Phi Z N by 60 into P by A. Okay. So already we have seen. So now EB is directly proportional to the, what is the depend? Number of conductors, this is constant. Speed, that is the variable. Flux, that is the depend on flux. North and south is a fixed one. So this is a fixed one, this is a fixed one, and if 60 is the fixed one, number of poles is the fixed one, number of parallel poles is fixed one. Now EB is equal, back EMF is directly proportional to the speed. So that's why here what will happen? So if the speed is more, back EMF also more. Initially back EMF is 0, that's why we draw the more armature current, that's why it will burn. That's why we are using the 3-point starter and 4-point starter in secondary level. Now what is happened? Here back EMF depend upon the speed, but in case of synchronous motor, the back EMF does not depend upon the speed because it is not self-starting motor. So we are started with the help of damper windings, or we can use the small AC motor or DC motor, that is the pony motors. But then, so how the back EMF is developed in the synchronous motor? So please tell it. So here the back EMF is directly proportional to the excitation of the rotor. So whatever the back EMF developed in the stator EB, so you can see here the back EMF is developed with the armature itself only. The speed also rotor speed. The speed and back EMF is belongs to the only rotor. But whereas in case of our synchronous machine, dear students, please observe here. What will happen? So here in this case, the back EMF developed is in the stator. That is depend upon the DC excitation to the rotor. DC current. One DC flux is given to this rotor. Due to this one EMF induced in the stator, that EMF is the opposite to the supply voltage. That's why you can say the back EMF. Okay. Now in this case, the back EMF EB is directly proportional to the excitation to the rotor. That means how we require the DC supply to produce north pole and south pole of the rotor. If excitation DC supply, DC source is given to the rotor, 100% of rate of the motor, we can say that is called normal excitation. Normal excitation. If the excitation is given more than 100%, then more DC supply is given to the rotor, then what will happen? It is known as the overexcited machine. Then if the excitation is less than the 100%, then we can say the under excitation. So what is the benefit of this, sir? Here what is happened? So here 100% is given. That is equal, the motor will works as a UPF, unity power factor. That means here you can see that here motor, whenever the DC supply magnitude changes, the current which is drawn from the supply, that is called armature current, drags the current from the supply, three-phase supply, in a unity power factor, lagging power factor and leading power factor. You can see the beauty of this thing. Now, if from the rotor, we are going to control the current in the stator from the supply. That means the armature current, here the armature current, whether it's a leading current, so what is the leading and lagging? So as we know that the three-phase supply voltage is this one, the current is always because I. So based on this one, the phi. That means the inductive coil L, we know that this is a voltage, this is a current, the phase angle between the voltage and current is, we can say, the power factor cos phi. The cos phi depend upon the angle between the voltage and current. So this current value maybe changes this angle based on the excitation to the DC. If DC excited at normal condition, then the current which is drawing from the supply is at unity power factor. That means the voltage and current are both in same phase, UPF. If in this case what will happen? The overexcited. So more DC supply is given to the rotor field, then it will draw the current, armature current, from the supply in the leading power factor. That means in this case the voltage is this one and the current is this one, I armature current, the leading power factor. And in this case what will happen? The less than 100%. So whatever the required magnetic field is required for the rotor, we are going to give the less than that one. So that means in this case the current which is drawing from the supply is a lagging power factor. That means the voltage is this direction, the current is this direction, I. Okay, the lagging power factor. That means here the current, armature current, can be varied. So based on the DC excitation. So dear students, so this principle we are going to use in our industries where we require to improve the power factor of our industry. Okay, so how can we are going to induce, and we can see it. Now based on this excitation, so we are going to produce the back EMF in the machine, stator machine. Okay, so what is this one? You can see here. Now the back EMF. So what is the formula? The back EMF in the motor in the three cases, EB, as already we have seen, E back EMF is equal to, so we know that, so root of, that is equal to, so here what has happened, once again you can see here. So in this case excitation condition, so in normal excitation, so in this case, so here the applied voltage is equal to V, the motor, we can see here applied voltage is equal to V and induced voltage is the EB. Okay, so induced voltage, that is dependent on the excitation. Okay, now so here if the voltage and EB are under normal condition, both are magnetically, magnitude is equal but phase out of phase 180 degrees, both are equal. Okay, what is the resultant? ER is equal to 0. Okay, the resultant is equal to this one. So what is the ER? We are going to write, already we know that ER, resultant voltage, is equal under square of, that is equal EB back EMF induced whole square. This is known as a EB, this is known V. EB whole square plus V whole square minus 2 into V into EB into cos, that is equal alpha. What is the alpha? It's the angle between the ER. We can see it. Okay, this is this one. Suppose in the second case, what is the second case? Second case, we are going to get the overexcited. That is the DC supply is going to the more. In this case, overexcitation condition, so voltage is this one. Okay, then so whatever the EB is given, overexcited leading current, the current is coming this direction, then automatically this EB is reduced here. That is equal here. This is known as alpha. Here you can say alpha. So what is the alpha? We can say this alpha is nothing but load angle. We can say alpha is equal to load angle, or we can say and coupling angle, or power angle, or synchronizing angle. We can say anything. Load angle, power angle, and coupling angle. Sometimes we can say synchronizing angle. What is a synchronized angle? Here you can, for example, you can take further. So here I am going to tell you. So here what will happen? The stator, and stator has the north pole and south pole. Okay, north pole and south pole. It's the axis is this one, and rotor has its this one also. Okay, rotor. It's the rotor has a north pole and south pole. Then what will happen? This stator axis and rotor axis coincide each other. Then what is the difference between the two? That is called alpha. That is equal 0 in this case. Okay. Suppose if load on the rotor increases further, then automatically so it will just shift to this direction. That means here the stator, you can see it, rotating magnetic field angle this one, and rotor dragged by the some angle here, that is called alpha. That is known as the load angle or coupling angle between the stator, rotating magnetic field, and rotor physical. This is called as alpha. So what is the purpose of alpha? Under no load condition also alpha presents. So to meet the some losses, stationary, that is the iron losses, and wind and friction losses. Okay, this is known as the coupling angle, synchronizing angle, or we can say is the power angle or load angle. So that is alpha is here. Okay. Now based on this alpha, now we are going to, so this is the resultant value, we are going to get it. This is equal to ER. This is the EB. This is a V. So the resultant R we are going to get that ER is equal EB whole square plus V whole square minus 2 into, so V into EB into cos alpha. So this is the angle. Okay. So that is a resultant. Once we are going to get the resultant voltage between the applied voltage, between the induced voltage, we are going to get that ER. Okay. So based on this ER can be changed based on our excitation. So what is the excitation? Back EMF changes. If under normal condition, EB under normal condition, okay, under case 1, so we are going to get that EB is equal to, we are going to get the root of, so V under whole square plus ER whole square minus 2 into V into ER into cos simply theta. Theta is the angle between the ER and V. We can say sometimes we can say that theta is the impedance angle. Theta, we can say theta is called impedance angle. So impedance angle, that means here we can say this is equal to R, this is called X, this is a Z, this is a theta. Okay. So the theta is equal, we can write it that indirectly. So tan inverse of, so this tan inverse of, that is equal to, we can write it, so x by r. Okay, so already you know that basic things. Now we can say the theta, that is the impedance angle, is a nearly this is a constant, because we cannot change z, we cannot change r, we cannot change x. So that is the theta in case of once the normal excitation condition. If under excited condition, less than 100% of the field is given to the rotor, at that condition EB is generated, is equal to, what's the formula? That is equal to V square. So you know the vector diagram, okay, don't confuse, based on the I am writing only. So what is this one? V, and this is the line, and this is the EB, okay, this is the alpha, a resultant of, so ER, okay, so and this is the current I, and V and I difference is of phi, and ER and I, this is the theta. So based on this one, we are going to calculate the what is the ER. Okay, simple, just manipulation of the vector additions, and we are going to write it. So what is this one now? EB. So back EMF induced in the stator when the field is given to the rotor under excited, less than 100% of the excitation. At that condition, what is the back EMF magnitude? That is equal, depend upon the V square plus ER resultant whole square minus 2 into V into ER into cos, that is equal theta minus phi. So what is the theta? That is the theta is equal to impedance angle. You can see this is theta, ER versus I, and phi is equal this minus this angle is the this one. Okay, if the excitation more than the 100% condition, what is the EB? Then EB under over excitation condition, so we are going to get that. So what will happen? Current will come this direction. Okay, simply here theta plus phi will come. Okay, V square plus ER whole square minus 2 into V into ER cos, that is equal theta plus phi, we are going to get it. Okay, so these are the three cases. Okay, three cases. Once here EB is equal to greater than the V, this is EB is equal less than V, here EB is equal to V condition. Three conditions we have seen this equation. Already we derived these equations in the previous classes. Okay, so these are the EMF induced in the stator armature winding with respect to the excitation to the rotor DC supply. Okay, so these are the things you know. So we after knowing this one, so armature current we already calculated, that is the current which is drawing from the supply, that is dependent on the ER by ZA. ZA is the, that is equal, we can write the RA plus J of XA. Okay, so this already you know that. Now what is happening in this? If the armature current, how it will changes? If load increases on this one, what will happen? As you know that the synchronous motor will runs at a synchronous speed only. That means 1500, suppose 4-pole machine, it runs at 1500 RPM only, otherwise 0 RPM. Not in 1200 RPM or not 1000 RPM it will run, because just like the binary case, whether it is 0 or 1 only, not analog. Analog, what is the analog meters? So from 0, 0.1, 0.2, 0.3, not in this case of synchronous machine. If you take the DC machine, what will happen? Under no load condition will run the nearly 1440 RPM. If the load is added to the on the road motor, then it will speed will reduce, that may be 1400 RPM. Further load added, then it will comes to the 1300 RPM only. Further load added, it will comes to the 1200 RPM only. Further load added, 1100 RPM only. So once load increased on the rotor, the speed will decreases up to minimum value. But whereas in case of our synchronous machine, the speed does not change irrespective of load. Sir, if the load added continuously, what will happen? It comes to the 0. no, in middle business. So up to some extent it will run. After that automatically, so it will stop. You can see here. So already we have seen that it is also. So there is a one graph also. What has happened? This is a graph. We taken the alpha in angle. We taken the torque developed in the machine. So because the current induced, the current produces the torque. So what is the torque? Now the torque we already know that this is going to the one wave. So we can say this is up to this one, the torque is maximum produced. That is we can the at 90 degrees. Okay, so the 90 degrees the torque is produced the maximum. Okay, after that what will happen? So the whatever the mechanical that already we have seen, P mechanical developed in the motor is equal to EB into V by so XA into sine alpha. So this is the final equation when the resistance of a armature is a very less compared with the XA condition. Okay, then what is happened? EB and V voltage into XA into sine alpha. Now we can see the mechanical power developed on the motor is directly from the sine alpha. If alpha is equal 90 degrees, it becomes to the PM is equal maximum. So that is equal 90 degrees. If alpha is equal 0 at starting, torque developed in the also 0 and motor developed power also 0. Okay, so that is equal alpha maximum is 90 degrees. We can say that alpha is equal 90 degrees. We can say that is the pull out torque. We can the pull out torque. After that it will goes to the down. As you know that there is a different type of the torques also present in our machine. So you are already very familiar the torques. So what are the general torques? So as you know, so the torque which is required to run the machine. Okay, the torque which is required to run the machine. As a student, you should know what are the different types of torques is developed. We know that the torque is the maximum pull out torque. Okay, so now similar to the different torque definitions in our synchronous machines are already we have seen. What do you mean by the synchronous torque? First of all, synchronous. What is the T synchronous? That means already we have seen that synchronous torque, it is the steady state torque required to drive the synchronous motor at synchronous speed. The torque is required to run the motor. So you should require some definitions of torque. What is a synchronous torque? It is the steady state torque required to drive the motor at synchronous speed. Now pull in torque. So pull in, what is the pull in torque? Pull in torque. That means it is the maximum constant low torque under which the motor will pull into the synchronism at the rated supply voltage and frequency when field current is applied. Okay, that is the pull in torque. What is the nominal pull in torque? So nominal pull in torque is at which the pull in torque at 95% of synchronous speed. Okay, at the same time pull out torque. What do you mean by the pull out torque? It is the maximum sustained torque which the motor will develop at synchronous speed for 1 minute. Generally it will ask in competitive exam, what do you mean by the pull out torque? It is a maximum sustained torque which the motor will develop at a synchronous speed for 1 minute. Okay, now pull up torque now. So it is the minimum torque developed between the standstill and pull in point. We know that the pull up torque. Okay, these are the different torques. So as we discussed previously, please go through these torques, different torques developed in the machine. Okay, now after that we are going to see that, so what are the a different excitation also depend upon the curves. As we know that very important one, the curves. What are the curves? That one. So here, so if excitation in synchronous machine, if DC excitation to the rotor changes, the current, armature current also drawn from the supply also changes its form factor. Now if DC supply versus armature and DC supply versus power factor, if you draw the curve, what is going to get it? As we know that once DC supply to the rotor, so by using the rheostat, we are going to supply to the DC to the rotor, and we are going to connect the 1 ammeter in armature. Then find that what is the current value with respect to the field current. If I draw the curve, so between the field current IF of DC supply and the current that is equal to, so armature current of the stator, then we are going to get it. So similarly, initially the field current is 0, the armature current also very high. Okay, please concentrate on it one. Once the field current here is minimum at this position, the armature current drawn from the supply is very high. The current increased, the DC supply increased for example 0.1 ampere increased. Then armature current in this case, in previous cases, for example, you take the 10 amperes. Now once the current increased from 0 to 0.1 ampere, here the current is reduced to the 9 amperes only. Okay, now further increased 0.2 amperes increased, then it is also reduced further, that is called 8 amperes only, and further increased 0.3 amperes increased here, then what will happen? It is going to the 7 amperes only. Is 0.4 amperes, it is going to the only 0.6. 0.5 amperes is going to the 5 amperes only. That means, so what you have observed here is that the initially this is the first one, the current is here. The current increased, here the current is decreased. Current increased, current is decreased. Current increased, current is decreased. Current is increased, current is decreased. That means here what is happening? We are going to get the current is decreased. Armature current taken from the supply is decreasing. IA decreasing, and the current is now increased. Now we can see the current supply to the field is a very low, but current taken from the supply is a very high. So that means we are going to get the some dropping characteristics. Now in this case, after knowing that once, okay, we have the some idea, if the field current increases, the current taken from the supply also decreases. That's why we are going to get the minimum current bill from the NPDCL people. So I thought that, so I am going to increase it further. Okay, so now I am the greedy, I want to reduce further current, then I am increased in DC supply further, then I am going to increase of 0.6 DC supply. Then what will happen? Here I can observe one thing. What I observed in this case, I observed that okay, I observed that the current is now once again increasing. 0.6 is going to the 6 amperes, once again it becomes the 6 amperes, and now further increases 0.7 increased, then it is also increased, 0.8 further increased, 0.9 further increased. That means here what will happen? The current is slowly from 0 to 0.5 amperes, the current is decreased armature current. Now I am going to increase further, but our armature current is increasing. That means here what is happening? So the current is up to one state, the armature current is decreased, and after one stage the armature current is decreased. That means at low excitation, at higher excitation, the current in the synchronous motor is very high. At one stage, the minimum current, armature current, that we can say this is known as the normal excitation. Normal excitation, whatever the required, that is enough. 100% is excitation in this one. If excitation less than this one, so we are going to get that more current from this one to this one. If the excitation more than this one, so the current also increasing. So decreasing, the current is up. So we are going to get it. So what is happening? So we got it one curve, that is equal field current versus armature current of stator armature. So we are going to get that. So one curve, this we can say this is a V curves. So this is the normal excitation, this is the lagging power factor, this is the leading power factor. Okay. So this is we are going to get the V curves based on this one. So how the armature current changes with respect to the field current we have observed. Okay. Now, so I want to take the another factor. What is the factor? Now I take in the armature current as a one factor. Now I want to take the cos power factor. Okay. So now in this case what will happen? So in this case, so I can draw the graph, same graph, and in this case we take the field current, excitation current to the rotor. Now in this case we take in the power factor PF of stator, armature current stator. Now what is happened in this case? Now initially whenever the current is equal to 0, the power factor in this case is also small value. If this increased further, the power factor increases. If field current increases, power factor also increases. This increases, this is also increases. This increases, this is also increases. So that means it is a changing this one. So it increases, the power factor also increases up to some excitation. The field current, the excitation to the rotor increases, the current taken from the supply is a leading, that is the current, the power factor also increases. Okay, so based on this one, I have some greedy to increase further. Then I am going to increase the field current further. Then what will happen? Our power factor from this one, it is also decreasing now. Further increase, decreasing, increase, decreasing, increase, decrease. Then we are going to get this one. That means now we got it a inverted V curve. This is a V shape, inverted V shape. Instead of this one, we inverted. So then we are going to test this one. Okay, so that means if the field excitation changes, the power factor as well as the current, armature current also changes its nature. Okay, that's why we are going to draw the performance of synchronous motor in the form of V curves and inverted V curves. Okay, so dear students, just already you know everything. So V curves can be drawn, the field current versus armature. So that means we are going to get this one. And whereas the field current versus power factor cos phi, so we are going to get it, that is called inverted V curves. Okay, so based on this performance, the machine performance we can analyze. Okay, this is the effect of excitation. So you know that due to the change in excitation to the DC rotor, so we are going to change the back EMF, resultant voltages, power factor and armature current. So once armature current changes, torque also changes. So what are the different torques? Already we know what is the pull-in torque, what is the nominal pull-in torque, what is the pull-out torque, what is the pull-out torque and pull-in torque and reluctance torque already we have seen. Okay, so these are the excitation. Now, so let us see, do some mechanical power equations. As you know that, so here what is happened? This is the stator, stationary part. This is the rotor. Okay, this is the north pole and south pole. It is a rotating magnetic field. Okay, now when three-phase supply is given to this one, it rotating magnetic field develops. Okay, so what is happened? It is the some winding inside. What is that one? So you know that this is a winding R phase, Y phase. We can say here. You can draw this one. So here is a R phase, Y phase, B phase, R phase, Y phase, B phase, R phase, Y phase, B phase. So the current is passing through this copper wire. So that power, input power, P input power is given to the motor. So P input is given to the motor, and that current from some current flows, power is used for the flows through the copper winding. So there is a I square, so R, copper losses. Then P input plus, and after that P mechanical. That means some of the power is given, some of the power is wasted in the form of the heat energy, that is I square R. Then total power minus these copper losses, we are going to the PM. So what is the PM? Power, mechanical power developed in the rotor, input rotor or output of the stator is equal to P input, mechanical input, that's what is the total input in electrical, minus, so three phases, 3 I square R A. So this is the first equation. Mechanical power developed, mechanical input to the rotor or mechanical output from the stator is equal to PM, that is called total input minus 3 I square copper losses. Okay, this is the PM is now developed. As we know that PM, the power developed in the motor. So already we have seen that we derived the equation PM developed for phase, PM for phase, already we have seen that. So big formula, what is that formula? Have you remembered? That is equal to EB into IA cos alpha minus phi. This is the for lagging power factor. Okay, for lagging power plus for the leading power factor. So we have seen this thing. The mechanical power developed in the rotor for phase is equal to back EMF into armature current into cos alpha minus phi for the lagging power factor, alpha plus phi for the leading power factors. Okay, so actually this is simplified form, and original, what is that one? Power developed for the phase, we can write, this is also we can write it, that is elaborate EB, so in the form of that is equal to impedance value. So EB into applied voltage by, that is equal to synchronous impedance, that is called cos theta minus alpha minus EB square by ZA into cos theta. So this is also we have derived in previous classes. PM we can write it simplified form or in elaborate form. So that is equal, that is called PM for phase is equal EB into V by ZA cos theta minus alpha minus EB square ZA cos theta. Okay, so this is a elaborate, and this can be simplified for the our calculation purpose when the armature resistance is a very low as compared to the synchronous impedance condition. We simplified for the our problems. PM is equal, we can write that EB into V by XA into sin alpha. Okay, so these are the generally used in our simple calculations. Okay, so this is the total mechanical power developed in the rotor. Okay, after rotor, so this is M of, so here we can see what is happened. So here PM is developed, this one. Now after PM, mechanical power is developed. So some of the power is lost in the friction and windage losses. Some of the power may be used to consume the iron losses, that is the constant losses, irrespective of constant losses. Then what is the net output mechanical power? So we can write it, that is equal to P net at rotor is equal to total mechanical power developed in the rotor minus constant losses. Constant losses. What are the constant losses? We can write it, this is equal to some iron losses, that is dependent on the voltage. Okay, iron losses plus some friction and windage losses. So because at the rotor there is a friction and windage losses in the bearings. So these are the losses. So by subtracting these losses from the mechanical input power, we are going to get that P net developed at the output of the motor. That is the HP. Generally we can say that this 10 HP, 15 HP motor, that is this is the net mechanical power developed. Okay. So these are the power flow from stator to rotor output. Okay. Now coming to the some interesting term also we used in our synchronous machine. What is that one? That is, so what is happened? Suppose now it's a mechanical energy generated. The mechanical energy, suppose this is the motor, synchronous motor. It is running. Okay, it is a mechanical coupled to our some motor, some applications. Now what is happened? Some load is suddenly added, this one. It will draw the current from this supply, and DC supply also given from the DC, and this is AC, 3-phase AC. Now the mechanical output is coming here, PM. Now what is done? So under normal condition it is running. Now I connected the one motor, I am going to couple to the another motor here also, mechanical, some application. Then what will happen? Suddenly I connected here, the load increased on the motor increases. Then once the load increases, rotor will try to retard. So that is the axis between the stator rotated magnetic field and rotor axis alpha increases. If alpha increases, armature current also increases. If the armature current also increases, torque also increases. So this torque is developed such a way that to meet the extra load on the machine. Okay, so this torque is developed such a way that to meet the extra load. So what will happen? More torque is developed. Due to this one, the rotor will, whatever the retarded, that is going to the meet this losses. Hence, so it will go to the overshoot the axis. Instead of this one, it is going to overshoot. Then suddenly the load is removed. At that condition, what will happen? Once again, alpha value changes. It will go to the new alpha value. Then automatically the torque required also has to change. Then alpha changes, armature current drawn from the supply also changes. It changes, then torque also changes. Then the rotor will retard. Once again comes to the back. Suddenly increases. Due to the load, maybe changes in the varying load on the motor, or some due to the frequency changes. What is the formula? So N is equal to 120 F by P. If the frequency changes, speed also changes. Because the motor is running at a constant speed. If the load added on the suddenly, load removed suddenly, the rotation changes, speed changes, or if the supply frequency changes, the speed also changes. In this condition, what will happen? The rotor, which is under normal condition running at a synchronous speed, due to the sudden changes of these values, the rotor will rotate at a overshoots and undershoots, overshoots and undershoots, that oscillates at a axis. This overshooting, we can say that oscillation takes place at rotor. This oscillation we can say this is a hunting of synchronous motor. Okay, so hunting takes place in the motor due to the use of synchronous motor for driving varying load, whether it may be a changing load, it may be frequency changes. So there is a possible to changes. If suddenly it decreases, alpha goes to a new value based on the preventing the hunting. Okay, so the rotor overshoots, oscillating rotor at a new position. So that purpose, so we can say this is a hunting. What is the hunting? By varying the load on the rotor suddenly, the rotor overshoots and undershoots, overshoots and undershoots. There is oscillation takes place. This oscillation of rotor, we can say this is hunting of synchronous motor. So there is a unadvisable. The how to recover this one, how to nullify this one. It may be occurred at any time. The frequency changes may be takes place at any time, and load suddenly some belt, coupling belt is suddenly breaks, and suddenly some load added that one. The rotor changes its retard and accelerate. So there is a possible to creation of hunting. How to avoid hunting? So as we know that the hunting can be nullified by using damper winding. Previously we have seen what is the damper winding. So damper windings, by using the hunting, can be nullified by using the damper windings. So already we have seen what is the purpose of the damper windings. Damper windings can be used for two purposes. One is the starting purpose, another is the nullify the hunting purpose. To nullify hunting purpose. So how the damper windings is used? As we know that once again, so whatever the rotor poles having the damper winds, damper bars, and short at both ends, that end and that end, and under normal speed, the rotor speed and synchronous or rotating magnetic field speed is 0. Both axes are coincide each other, alpha is equal 0. Once hunting takes place, for example, and there is a possible to alpha presents, then so due to the relative motion between the stator magnetic field and rotor field, there is a, as per Faraday's laws of electromagnetic induction, the EMF induced in the damper windings. The damper windings are shorted both ends, then rotor current will, that is the damper current will flows, it produces its own magnetic field. The field produced such a way that it opposes cause of its production as per Lenz's law. Then so here what is the cause of this one? Oscillation purpose only. Under normal condition, so relative motion between the rotor damper windings and rotating magnetic field is 0. Due to the variation, the sudden load changing, the rotor and rotor conductors and rotating magnetic field, the relative motion takes place. That's why it induces its own EMF due to this one current, eddy current. Due to this current, the flux produced in the damper windings, the flux is always opposite cause of its production. What is the cause? Is the vibrations. The vibration will nullify as per Lenz's law. Okay, so that's why so we are using the damper windings two purposes, one for the starting purpose as well as for the hunting purpose. The hunting takes place only synchronous motor only. Please remember, my dear students. Okay, so these are the some special things you have to remember. Now coming to the application point of view. Generally, what are the applications of synchronous machines? So very important applications is the mainly power factor improvement purpose only. Okay, so what is the power factor? How they are going to increase the power factor? As we know that the power factor can be increased by changing the excitation. Now let us see the main applications of synchronous, because it is a costly machine. Okay, so what are the applications? Applications of synchronous machine. So main applications are, one is the power factor improvement purpose, PF improvement purpose we are going to use, power factor correction purpose. Okay, second one is the generally where we require the constant speed is required. For example, in paper mills, rolling up paper mills, are constant speed and constant load drives. Constant load drives we require. At that condition we are going to use, and at the same time it can be used for the voltage regulation also in transmission line. Voltage regulation times purpose we are going to use it. Okay, so these are the how you are going to use the power factor. As we know that the overexcited synchronous motor having a leading power factor, that is the synchronous condenser. So here we can see, so when EB is greater than the V as a overexcited, then the synchronous motor under minimum load or no load, we can say no load, and DC supply is more, then it acts as a synchronous condenser. When it becomes a synchronous condenser, it generates the reactive power energy. Okay, that is reactive power energy. So overexcited synchronous motor having a leading power factor are widely used for improving the power factor of those power systems which employs a large number of the induction motors and transformers, where these induction motors and transformers consumes the large amount of the reactive power energies. Okay, and other devices having a lagging power factor such as welders and fluorescent lamps, etc., etc. So those where we require the more reactive power is required, we can operate our synchronous motor under no load condition with overexcitation, then it will generate the large amount of the reactive power energy, and this is compensate the where these machines consume the reactive power energies. That's why we are going to improve the power factor. Okay, now where we require the constant speed applications, so we can use it is because of higher efficiency and higher speed. So here synchronous motor where having the speed more than the 600 rpm are well suited for loads where constant speed is required. Okay, so that means here where we require the more than we can say here if the speed synchronous motor speed is greater than 600 rpm or well suited for loads where a constant speed is required, such as centrifugal pumps, belt driven reciprocating compressors, blowers, line shafts, rubbers and paper mills, etc., where require the constant speed. At the same time, the synchronous motor where we require the less than 600 rpm are used for drives such as centrifugal and screw type pumps, ball and tube mills generally used in our thermal power stations, vacuum pumps, chippers, the metal rolling mills, etc. Okay, these are some applications already we have seen. Now at the same third point is for the voltage regulations. The voltage at the end of the long transmission line varies greatly, especially when the large inductive loads present on the system. When an inductive load is disconnected suddenly, the voltage tends to rise considerably above its normal value because of the capacitance effect. By installing our synchronous machine with a field regulator for varying its excitation, this voltage rise can be controlled. If require the more reactive power is required, then we are going to overexcited. If we require the suppose suddenly the inductive load is disconnected, then we require to consume that reactive power in the lines due to the capacitance effect of the long transmission lines. At that condition, under excited condition, will draw the lagging power factor. That's why, so we can, if required, we can increase reactive power. If required, we can consume the reactive power from the lines. That's why we are going to maintain the regulation of our transmission lines. Okay, so these are the some applications of our synchronous machine. Okay, now after that, how we are going to improve the power factor? If all, so because we already done some problems. how this kVA active power and reactive power and operating power changes in the system. Already we have done some problems, already we have done some calculations also. Let us summarize here also once again. So what is happened? So here for example, you take, so this is a one line, okay. So now it is connected to the induction motors and it is connected to the transformers. Now once these are the both are inductive nature, it draws the reactive power, more currents with the lagging power factors. Now what is happen? So due to this one, so we are going to get it. So reactive power, that is we can see the two motors in a industry. I am going to, so one transformer, some induction motors, it draws the current of this one. So then what is we can say what is the active power? Kilowatt. And what is the reactive power? kVAR 1. What is the operant power? kVA of this our load. Okay, now the power factor always less. Now I am going to install my synchronous motor for the same in my industry, connected the SM. Now it will draw some current from the supply. Then what is the power of the synchronous? This is the kW2 active power, kVAR 2 reactive power, and kVA 2 is the operant power of synchronous motor. Now it can generate the reactive power, it can consume the reactive power. And what is happen? Whatever the reactive power required for the local is supplied from my synchronous machine. Okay, then automatically the demand from the supply is reduced for supplying the reactive power. That's why, so what will happen? My overall power factor increases sum of these two. This is a basic concept. Okay, as we know that, so here what is happened? This is the power triangle, the kilowatt, kVAR reactive power, this is the operand kVA, this is the angle. Okay, for each value, so we are going to do this one. Now after drawing this one, we are going to draw the one vector diagram. Let us take one vector diagram here, simple vector diagram. So let us take it. Okay, now this is a one graph. So the one is a line, this is the one induction motors, and this is my SM synchronous motor. Okay, now first the machine 1, machine 2. So machine 1 will draw the what is the active power. Let us assume that the machine 1 is taking power here. So this is taken this is equal kilowatt, kW1. What is the reactive power here? So this is equal, you can take it as a line. Okay, sorry, we can take it, this is equal kVAR1. now this is the kVA1 of my machine. Okay, now second case I am going to take it my synchronous machine value. Now we know that synchronous machine is a overexcited, it is act as synchronous condenser. At that condition it draws the leading power factor. Then kilowatts, what is the power rating? Is the kW2. Now we know that is a reactive power, kVAR2. Now we connected here, kVA2. Okay, that means here you can do the kVA, the positive kVAR positive direction, this is the kVA negative direction. Okay, now this is induction motor, this is synchronous motor. So resultant of we are going to get it, that is the another one, so you can take it. Now so here what is the power? Total kilowatt is equal to, we can write it Okay, we can take it. We can take it. Now, what is the total power? kWt total is equal to kW1 plus kW2, total 2 powers. And reactive power also, kVART is equal to, what is the kVAR induction motor plus kVAR2. Okay, so this is the reactive power. Now, what is the kVA? kVA total apparent power is equal to kVA of induction motor plus kVA of synchronous motor. These are the equations we know. Similarly, now you can see this kilowatt 1 plus kilowatt 2. Then what is the resultant value we are going to get it? You can see, we can draw the graph. Now, based on the kilowatt, this one, so we are going to get it. This is for example, so we are going to get it, for example, this one. This is kWt total. Now, so this value and this value minus this value, we are going to that one. So now we are going to get it. This is this value. Okay, that is equal kVART, this value. Okay, now this value is, can write it, this value. Okay, now angle is the phi. That means you can observe here that what you are going to observe here, you can see it. Okay, you can see it. So initially this is the large value and this is a large value, and this equal to this equal, we are going to the very less value. That means here reactive power consumed from the supply is reduced from this value to this value only. Okay, so that's why we are going to improve the power factor. Okay, so based on this one, we calculated some problems also, you are very familiar. Okay, so this is a synchronous motor. Now, what are the advantages of synchronous motor? So we know that advantages. Advantages. What are the advantages? Advantages, first one is it can be used for power factor correction purpose. Can be varied power factor based on the excitation. And what are the advantages? Another is the speed is constant. So where we require the speed is constant irrespective of load, then we can use this type of the machine. Okay, now coming to the disadvantages. What are the disadvantages? What are the disadvantages? So as we know that first one is even we are given the DC supply, AC supply and costly machine, but it is not self-starting. It inherently not self-starting. Self-starting, not self-starting. Okay. Second one is so here what is happened? We require a separate excitation is required for the DC. Need a separate excitation. DC supply is required for the rotor, and hence we require the initial cost is very high as compared to our DC machines and induction motors. Cost is very high, and it cannot be used for varying load, where we require the various load. At that condition we cannot be used. Okay, varying loads. If overloaded, and it automatically stops. So it runs at synchronous speed or 0, but if some load is added more than 90, alpha is equal to 90 degrees, then it comes to the 0 position. And it has also one problem that is called hunting problem takes place in the machine. These are the some disadvantages. It is not self-starting motor, needs separate excitation, initial cost is high and cannot be used for varying loads. If overloaded, it automatically stops and it has a tendency of generating hunting. Okay, so these are the some disadvantages of machine. So dear students, these are the some advantages and disadvantages. Okay, now let us summarize what we have seen in this class. I think this is the total nearly that 6-7 periods summarized here. Okay, so let us summarize what we have seen. Okay, what we have seen. So here we have seen the advantages and starting methods. In advantages, we have seen the speed regulation is 0, it is not self-starting, it can be operate wide range of power factor, the armature current depends on the excitation, and its armature current value is very high at low and high excitation period, and over excitation of synchronous motor is used as a power factor correction, already we have seen. And methods of also starting we have seen by using the AC DC small motors, starting as a induction motor, and damper windings also used. The damper windings on the rotor poles acts as the rotor reaches a 95% of the synchronous speed. We have given the DC supply to the rotor winding. And we have covered also the different type of the torque definitions. Synchronous torque, it is the steady state torque required to drive the motor at synchronous speed. We have seen pull in torque and normal pull in torque and pull out torque and pull up torque and reluctance torque also we have seen. And we have seen also load angle or power angle. It is the space between the axis of the stator rotating magnetic field and the rotor pole axis we have seen, that is equal to alpha. Okay, then we can say the synchronous angle also we can say it. The effect of change in excitation we have seen that based on this one we are going to draw the V course and inverted V course also we have seen. And at the same time we have seen that so the speed, that is ns is equal to 120 F by P, and it is electrically identical with the our synchronous generator. So and we have seen that the armature current varies with the excitation. It is a very high and low at initial position, already we have seen. Okay, so what are the highlights of this one in synchronous motor comparing to the alternator? The field is rotating in this case and armature is a constant, and the frequency of this machine depend upon the Pn is equal to 120 F, and we know that in the generator E is equal to 4.44 F 5 T, and Kc and Kd distribution factor and pitch factors, and that is the in case of synchronous alternators. And short pitched coils also used in synchronous generator for the sinusoidal purpose, and the stator of the alternator is connected in star to reduce the number of turns per phase in general alternators. So here you have to remember starting methods. We are going to use the star point should be shorted. The percent of regulation is equal to no load speed minus full load speed by full load speed into 100%. That is the regulation of this one. And flux in the air gap is not constant and is varies based on the armature current as we seen. And the power factor depends upon the excitations. The angle between the synchronous rotating magnetic field and the rotating poles of a synchronous machine is called the synchronizing angle, or we can say the load angle or coupling angle. If the mechanical power of one alternators, if the two alternators connected is parallelly, if the mechanical power of one alternator changes, then its kilowatt rating changes. If the excitation of the one motor changes, its power factor and kVA changes, as already we have seen. And synchronous condenser over excitation with no load, and the hunting is a synchronous machine can be prevented by using the damper windings. Okay, so as we know that the mechanical, that is electrical angle theta electrical is equal to theta m by into p by 2, the poles by 2 already you have seen. Okay, the pull out torque of a in a practical synchronous motor will occur when the torque angle is equal to nearly 75 degrees. Okay, so dear students, these are the all salient points already we have covered in previous classes. This is a summarization of all total synchronous 2 lessons. Okay, please go through this one. Okay, thank you for listening this thing.